Good afternoon. My name is George Paris. I'm working on a series of videos on the topic of thermodynamics. I've written a book. The videos are closely tied to the book. And this particular is the second slide, or the second video in the series, and it's going to deal with entropy, enthalpy, and free energy. The reason for taking them in that order hopefully will become apparent. Now, in the first video, that is to say part one, I talked about heat and heat capacity in quite a bit of detail, and a lot of you may not appreciate why I spent that time doing that, but by the time I'm finished with the third and fourth videos, I think it will all come together. In any event, this is going to be the heart of what most chemistry classes in college deal with: entropy, enthalpy, and free energy. I take it from a historical standpoint. When I do these studies and try to understand things, I go back through the history so I can see how the ideas developed, and I figure if I can see how the guy first figured it out, maybe I can understand it as well. And so there's quite a bit of history here. Some of the slides are, well, pretty much all the slides are quotes directly from the book, or very closely quoted from the book. And so there's in some cases a fair amount of development of a history. Now, history is very complicated. It moves forward, it moves back, it moves sideways. There are parallel channels, people going different ways in different channels. People in Russia may not know what people in Germany are doing. People in English may not know what people in France are doing. So you end up with a really very complicated picture. And what I'm going to try to do is knit all that together. Especially in the book, I did that. But here, I am not going to take the time to read all these slides because some of it is, it turns out to be irrelevant to the bottom line. But I do think it is important to understand where it came from, and I've included it in the book, and I've included it here. The book is available on Amazon.com. I'll probably mention that a few times through the process here. In any event, let's get started here. All right, now generations of students, and this is sort of my pet peeve where I'm coming from in this whole process. Generations of students, including me, we're taught to be practitioners of thermodynamics. We're not really taught to understand thermodynamics. Most students, professors of chemistry, textbook authors, etc., never do more than memorize the Gibbs equation and learn how to take data from standard tables and plug it into the equation and calculate free energy for a reaction. The reaction will go spontaneously if free energy is negative. It will be in equilibrium if it's zero, and it will go in the opposite directions if the free energy is positive. Okay, I've spent many hours over the last 50 years trying to understand what free energy is and why this equation works, and I hope to have it right now, and I hope I can explain it to you. All right, go back to some basics. Conservation of energy. Here again, I'm looking at historical time. And I think the important point here is that although people were starting to talk about conservation of energy early 1800s, it was really not until the mid 1800s, or in 1847, that you had luminaries such as Hermann von Helmholtz got involved. People accepted his explanations and held him in high esteem. And it was not until that time that people really accepted the idea of conservation of energy. One of the reasons for that was that we didn't understand what heat was, and didn't understand that you couldn't take an infinite amount of heat out of a substance. Like coal could just keep going. Is sort of the way people thought at one point. So once you understand that there's a certain amount of heat in a substance, that is there's something called absolute zero. Once you understand that, then you can realize that, hey, we must have something. All this stuff has to balance out. And that's sort of going to be the theme of what happens here in the next few slides. Now, here again, going back to the 1800s, one of the things you need to be aware of, especially is when you read current textbooks, is that people like Watt and Carnot and Joule were all very much involved with the Industrial Revolution, heat engines, etc., which provided a major impetus to study thermodynamics, but they did not really care about the molecularity of it, because nobody, in the 1800s, early 1700s, people were still talking about air, earth, fire, and water. So it was quite a ways before coming up with some reasonable theory. Now, the theory which I guess Lavoisier was very influential with was the so-called caloric theory. At this point, we started to understand what elements were, but heat was still a mystery, and Lavoisier and his contemporary engineers, Watt, Carnot, etc., those guys viewed heat as a fluid that sort of flowed through matter, and they talked about it flowing from one reservoir to another reservoir. And this was embraced and used by the engineers, and that's why you'll see Carnot diagrams in all your chemistry textbooks. All right. So the caloric theory, which is not very useful, I think, for chemists and physicists and material scientists and biologists, view it this way. Okay, here's, this is the bottom line. This is the steam engines and industrial revolutions coming full force. The engineering concept of heat as a fluid led to much difficulty in coherent discussions of thermodynamics from a molecular standpoint. Okay. All right. The molecular kinetic theory of gases, it was slowly accepted. Okay. People didn't know what a gas was. It turns out that Bernoulli, early 1700s, actually came up with an idea that made sense, but he was so far ahead of his time, nobody paid him much attention. There was a guy named John Herapath, also did not get much attention. He's not a scientist whose names you recognize. A fellow by the name of James Watterson, John James Watterson, also was not very well recognized. It was not until some highly recognized scientist, in this case Helmholtz, got involved that the kinetic theory of gases was well accepted widely within the scientific community. And we're talking 1856, whereas Bernoulli was actually probably 120 years earlier. All right. So it took until 1856 before people really accepted the kinetic molecular theory of gases. All right, the absolute energy of a system. Here's where we get into it. Now, the way I'm going to define it, and I'm anticipating some of these historical developments. The absolute energy of a system is the sum of all the energy that goes into a collection of molecules, assuming that the starting point, absolute zero, is a collection of individual atoms in space surrounded by a medium of constant pressure. And this absolute energy is given at a standard temperature, T sub 0, this capital T sub 0. To me, that's an arbitrarily chosen standard that people consider. And this absolute energy really is built up of three parts. Okay, first off, there's the potential energy associated with formation of bonds at absolute zero. If you had things reacting at absolute zero, that's indicate that the energy involved at absolute zero, E0, is the potential energy associated with bonds. Then you have thermal kinetic energy associated with raising the molecule from absolute zero up to some standard temperature, T sub 0. Okay, this includes thermal energy and energy associated with phase changes, which is also thermal energy. This definition necessarily includes the thermal energy, kinetic energy, which is in the form of translations, rotations, vibrations at the standard temperature, T sub 0. All right. Now, the work required to create a volume or space is the third elements. So if you start off with some atoms and make molecules, you have to eventually create volume for that to exist. And that volume that they create to exist is a work term. Basically, it's a work done on the medium, And it's P, the pressure, constant pressure, medium times the change in volume that's associated with creating the system. Okay. So keep that in mind. Keep those three parts in mind and appreciate where I'm going with this. Now, I've got a series of figures below. You can't see them yet, but they'll be on the next slide. The first figure will be on the next slide. And I've tried to graphically capture this, okay? In the first graphic, I defined zero energy as a state of separate point masses of atoms with no kinetic energy except that required by the uncertainty principle. In other words, we're at absolute zero. The atoms are thus at absolute zero with a temperature of zero and a volume of zero. And they're under a constant external pressure. All right, that's the starting point. I've got a bunch of point masses, no kinetic energy, they have no volume, and they're just there. And the first step of this process is to form molecules from these atoms. Okay, what you're going to do is you're going to form bonds, and that energy involved in forming those bonds is going to be E sub zero. Okay, so let's go look at what that looks like. Okay, here is the first step in a multi-step process. Over here on the left-hand side, I have an energy scale, and I've arbitrarily identified zero on that scale. And then in the initial conditions, I have atoms. The pressure that they're exposed to is P. The temperature is, I'm defining it as zero, which is absolute zero in the real world. And the volume is zero. They don't occupy any volume at this point. Now, when they react, I want to keep the system at zero temperature. When they react, those atoms react with one another to form molecules. There's going to be bond energy released. In other words, atoms don't react to form molecules unless it's a favorable process, unless they can reduce their overall energy. And so when that happens, there's going to be energy released from the system to the surroundings. And that in order for the system to remain at absolute zero, there must be energy leaving, and that's that broad red arrow, E sub zero, that comes out of the system and goes into the surroundings. So that the system, in my definition, can remain at T equals zero, the volume is still zero, and there's still an external pressure P. All right. Now let's step ahead. Now, unfortunately, I screwed that up again. I don't know how I did that. I'm still blocking some material. In step 2, we're going to put thermal energy into the molecules. All right. This requires an input of energy, which is calculated by multiplying the heat capacity constant volume times the temperature, the change in temperature. And if we assume that we started at zero, the delta T is going to equal to T, okay, because T minus zero is T, okay. So for real substances, the C sub V is a function of T. And in the figure below, the average C sub V is taken as a temperature range from 0 to the standard temperature. Now, the thermal energy can be calculated by multiplying the average heat capacity in the range 0 to T sub 0. That would be the average heat capacity from 0 to T sub 0 by T0. Okay, if you had the average, you just multiply it by the final and you get the actual average amount of energy. Okay, now, so you have this equation here where you've got the average heat capacity is integrated from 0 to T sub 0. That's actually supposed to be a sub 0, but I can't do that with the way the typewriter works. It's a change in heat respect to time, or temperature, excuse me, divided by the change in temperature, and it's all integrated over dt. And I could simplify my terminology that change in heat over change in temperature is going to be C sub v as a function of temperature integrated over dt. And I'll just call that S. That looks like the integration function from 0 to T sup 0. Okay, multiplying this average heat capacity, S, by the standard temperature T sup 0 gives the absolute heat content, thermal energy, at T sup 0. Okay. Now, some of you who have studied thermodynamics before will start to get hints of what's happening here. Okay, this definition necessarily includes the thermal energy, kinetic energy currently in the system, translations, rotations, and vibrations at the standard temperature. Why is this not going? Oh, I don't got underlined. All right. Okay. Now we've made the next step. Okay. In order to put energy into these molecules, obviously that's going to be an endothermal process, and my T times C sub V T, that's the average C sub V, is going into the system, and so that's going to raise the energy level of my molecules. So I went from, I've still got pressure still constant through this whole process, P is still equal to P. My T is now, it went from absolute 0, T is equal to 0, to some standard T is equal to T. And my volume is still 0. I have not changed the volume of the system. So I've now added this energy, and I've got a new energy level for the whole system. And that energy that was added is T times C sub V, where the C sub V is the average heat capacity over that range. All right, now we get to the sort of the bottom line here. The last thing I'm going to do is I'm going to let this system expand to its, whatever appropriate volume it should be, and it's going to do work. I have to put work into the system, have to put work into the molecules to make them expand against the external pressure. And so now I have, put a term RT into here. This is the heat of the change in volume against constant pressure. And so now at the end over here on the right, I now have the situation with the molecules is there's a standard external pressure, P. We have gone up to some standard temperature, T, and we have occupied a volume, V. Okay, so now I've got my absolute energy, which based on the quantitative amounts that I drew here, is different from the energy that was there at absolute 0. Obviously, I've just used arbitrary numbers here, or arbitrary amounts, but this sort of gives you a stepping stone. So if we were going to define, for example, the free energy of the system, that is the absolute energy of the system, at PTV, the current pressure type, we would be looking at that amount of energy that is between the blue line, the horizontal blue arrow, and the black line below it. This is a fairly useful diagram. I would suggest thinking about this a lot. All right, now let's talk about one of the icons of this whole process, a fellow by the name of Clausius. On the next couple of slides, I've got a fair amount of his background, some of which is not necessarily very relevant to our discussion. But realize Clausius was born in 1822, died in 1888. This was sort of, at the time of his birth and by the time he was a young man, the Industrial Revolution was in full swing, and he was interested in the heat involved in these processes. But remember, we had not yet established that you have conservation of energy at this point. We didn't know absolute 0 at this point. So he was sort of poking around in a very dark pile of data. And, it wasn't until, I guess it was about 1848 that Lord Kelvin got involved. Other people had talked about this, but, Boyle, Lambert, etc., had estimated that there was an absolute zero, and they thought it would be about minus 270 degrees Celsius. This was based on volume measurements of gases as they changed temperature. And but this is one of those ideas that until you get somebody who has some clout in the scientific community, in this case, Lord Kelvin, you don't really get the idea spread around a lot. So it was not until about 1848 that people accepted the idea that, hey, there's an absolute zero to temperature. Now, this had a big impact on Clausius thinking. Okay, once you accept that there is an absolute zero, Clausius concluded that we have consider a system at ambient temperature. We must account for all the energy that went into this to raise it up to that point. Interesting idea. But it was not until 1865 that Clausius suggested a general mathematical form for the thermal energy involved in taking a system from absolute zero, T is equal to 0 degrees Kelvin, to its current state, that is ambient condition of T sub 0. He may have been motivated to do this because at this time, about in the 1860s, people were starting to do heat of reaction experiments. They were doing calorimetry. And so it's like, okay, how does this calorimetry stuff, the data that is getting there, relate to what I understand to be the energy we need to raise something from absolute zero to some standard temperature? That was the way he was approaching the problem. And this we're talking 1865. And what he ended up doing was he said, okay, my heat capacity constant volume is a function of temperature, and it's also what we call dq over dt. dq is the heat, change in temperature, okay? Now, the way he expressed this has been confused, I think, in some textbooks and even scientific papers. The heat capacity average between 0 and T sub 0 is going to equal to this integral of C sub v, which is a function of T, divided by T, which is this is the constant. This T sub 0 is not a variable, it's a constant. So if you pull that out, if you could take that and multiply it through this, if you multiply this equation through by T sub 0, the T sub 0 would end up over on the left-hand side multiplying C sub v, and you would just basically have C sub v T times dt as that integral. So here we go, and we continue with that. So if we plot this on a graph, we realize that as we change the temperature of a material from absolute zero to some standard temperature T0, we're going to put energy into it. And we're going to go through solids, we're going to melt it to liquids, we're going to go liquids to vapors and vapors to gases. And so we've got all this these. Not only do we have heat capacities of materials, of phases involved, we also have latent heat involved as we go through this process. And so his integral takes into consideration all of these factors. Keep that in mind. He's integrating across this entire thing. He hasn't explicitly talked about the different pieces, but it includes all these pieces. His average heat capacity includes all these elements, and it's basically a straight line that runs from zero to the final energy. Okay, now I think this is where one of the places where I start skipping material. But obviously the energy that the system contains at this standard temperature T sub 0 is going to be the T sub 0 times the average heat capacity. All right. So we could use that equation, or we could go like this. Now, I'm going the quote on the left, the stuff in italics, is actually quoted out of one of Clausewitz' papers and explains why he called it entropy. And it also plays off of why people were calling things enthalpy. But in any event, if you look at his graph again, his integral, this mysterious integral, is actually just the average heat capacity from 0 to the final temperature, whatever T sub 0 happens to be. So you've basically taken a series of complicated functions and you turn it into just one number, which makes it easy to do the arithmetic. Now, he called this the transformation factor. I believe he would have been better off if he just flat called it the average heat capacity. Of course, I mean, there's reasons why he wouldn't do that. Now, there's some very sloppy pedagogy going on out there. I find that some books and professors where you take the term S and we'll call that entropy. And obviously S has the units of energy per mole per degree Kelvin because it's really a heat capacity. And then others will use the term TS, that's the product of the temperature, some standard temperature, times the S, and we'll call that the entropy because now we have an energy term. So, using that, calling both of these things entropy is very confusing. I think that would have been much better had we called S the average heat capacity, and the TS would be the energy entropy that Clausewitz was referring to. Now, this gets confused even more when you start talking about Boltzmann's ideas and other things. Now, it should be obvious that the term T times this S, this integral between 0 and T, is as defined by Clausewitz, is the absolute amount of thermal energy plus the PV that I have called out in the absolute temperature above. Now, if we look at, one thing that may hit us here, we may say, hey, look, there are some solids that are presumably solids at absolute 0, these crystals, and they're going to be solids at ambient temperature where we measure things at like 298 degrees Kelvin. And so if they are the same phase, they probably don't change the heat capacity that much over that range. And so wouldn't there be a correlation between the theoretical heat capacity that we calculated earlier when we were talking about molecular motion, which is the number of molecules times 3R, 3R being the heat capacity of a single molecule vibrating or single atom vibrating in a lattice. And then we'll look at that times the actual heat capacity that we measure at 298 degrees Kelvin. People have done that. That's an experimental number. And then the entropy, which is determined various other ways, from equilibrium, things like that, we can look at that entropy number. Shouldn't they all be the same? Okay. Well, there is some correlation between theory and reality here, but the reality is we're not, when we look at entropy today or at a particular temperature, we're not able to take in consideration the flexibility of the lattice, whether or not that initial assumption about the heat capacity being correct, etc. And so if you look at these data, you'll notice that they're pretty much on the same order of magnitude, which is useful. But there is, most of the time you have variation. Now, what I've done on the left here, I organized, this is related to a table that was in the first video. But what I did here is I took and I organized these crystalline solids by their melting point. In other words, aluminum trichloride has a melting point of 453 degrees Kelvin, and you go all the way down to magnesium oxide, which has a melting point of 3,125 degrees Kelvin. So you're basically you're getting more and more stable crystal lattices as you go down. The systems are bound together more tightly. Now, if you look at the calculated N times 3R, that would be the theoretical heat capacity, assuming that these all worked right. You'll notice that they jump around a bit based on the number of atoms, because N3R is all that matters is how many atoms you're looking at per mole, or in this case, ions per mole. So if you got 3 ions, you got 3 times 3 times R. If you have 4 ions, you've got 4 times 3 times R. So that's where those numbers come from. In the case of aluminum oxide, you have 5 times 3 times R. Okay. All right, so there's your theoretical heat capacity. Your actual measured heat capacities at 298 degrees Kelvin are less variable because they're more based on reality. They sort of average out the variations based on stability of the crystal lattice. And then your entropies are, again, variations. Turns out that something like sort of in the middle here, like sodium oxide, you'll notice that the theoretical heat capacity is 74.8. The actual heat capacity at 298 is 73.0. And the entropy at 298 is 73. So that would be a perfect example. Unfortunately, reality is not that simple. And the trend, if you look over at the entropies, the trend is that the more stable the crystal lattice, presumably the less vibrational opportunities you have, which drives the heat capacity down. And with heat capacity being driven down, you are getting an entropy which ends up substantially below what you might calculate otherwise. Okay. So the heat capacity, the entropy tends to drop as the crystal lattice becomes more stable, because you lose. I think what's happening is the steps. If you're thinking back about the vibrational or librational energy level steps, they get bigger as you go down, and so at 298 degrees Kelvin, you have very low population of the higher steps, whereas for magnesium oxide, but you have substantial population of the higher steps in the case of aluminum chloride. And so if you look at this thing on the right, in most cases we're trending downward, consistently downward. Okay, next slide. See if I can make it over there. Okay, let's look at products and reactants for a moment. This would be two different systems. The products and reactants, they may be linked together in a chemical equation, but they don't really have any association in terms of thermodynamics. They are different substances. They have different heat capacities. They have different physical properties of all sorts. And so we really are looking at two different systems, A and B, which have different pathways, different latent heats of of melting and fusion, vaporization, etc., and different heat capacities in those phases. And what I've drawn out here is I have two different pathways, and you'll notice that B ends up above A in this particular drawing. And so it has a heat capacity, an average heat capacity that is larger than the average heat capacity of A. And so the difference between B and A here is going to be T times the change in delta S. In other words, the difference in that slope times the temperature at that point. Okay, that's what that vertical green arrow represents, is the difference in entropy between A and B. All right. And again, if you've studied thermodynamics very much, you know where we're going with this. All right, let's go back, and this becomes even sloppier and more complicated because more people are involved. We're going to talk about enthalpy. And enthalpy came about through mainly through a concept of doing calorimetry, measuring the heat that is generated in chemical processes or physical processes. Now, enthalpy is actually a relative number. It's measured in kinetic potential and work energies that are stored in a system at various temperatures and pressures. It may not be obvious, but you cannot, the heat gain or loss of system during a chemical or physical change at a constant temperature has no real relationship to the absolute temperature in the initial system and the final system. Okay. So, going back into history here a bit, heat and energy had long been considered from, long before 1900. And we've been talking about this for 2,000 years. There was the phlogiston theory, it gave way to the caloric theory, etc. And for a long time, people were fooled because of the lack of understanding of what they were measuring. They were fooled into thinking that the things they were measuring in calorimetry were absolute numbers, and they're not. We go back to mid-1700s. Joseph Black started doing experiments with freezing water and melting water. He realized that if you mixed water and ice together, that they would always come to 0 degrees Celsius. They would equilibrate at 0 degrees Celsius when in a mixture of ice and water. That was interesting. If you put some heat in it or took some heat out of it, the amounts of ice and water would change, but you would stay at 0 degrees Celsius. Now, Black was getting to the end of his career. He collected data until about 1766, but in the meantime, he talked to James Watt. This is actually a famous drawing of Black talking to Watt. They both were at the same college. And the history of this, obviously we went from the phlogiston theory, 1750, caloric theory, 1790. Kinetic theory didn't take hold till 1860. In the middle, the engineers grabbed the caloric theory and ran with it by 1820. Excuse me. All right, now it really starts getting complicated because people are not even involved in the experimental work and were involved in passing information back and forth. The point of this discussion, basically, eventually, the ideas got from Black got over to Lavoisier. Okay, took a couple of steps to make that happen, but Lavoisier over in France, late 1700s, picked up the idea that there's heat going on. And Lavoisier was a man of means, and he had friends like Laplace, and they got together and they said, let's build a calorimeter like the one that Black had. And this calorimeter, it's what's called an ice calorimeter. What you do is you have a multi-wall container. You have your sample container in the center of this whole thing. It is going to be surrounded by ice, which has been equilibrated with ice water on the outside. So the outermost jacket of this system contains ice water, which is at 0 degrees. You put your sample container, you put ice into this, pack it around your sample container, which is in the center there, and you let it equilibrate such that obviously as long as the ice is melting, it must be, the heat from the sample and all this stuff must be above 0 degrees. But eventually, if you keep your ice in the outer container, this is equilibrated with water, you can make sure that the ice then equilibrates at 0 degrees, and you stop having liquid drip out the bottom because the ice is not melting, because There's no heat going into it. All right. So eventually here, what you're going to do is you're going to do things in that innermost container, that sample container. Uh, you know, do things there which are going to cause heat to be released to melt ice, and then you're going to have ice that's melted come dripping out the bottom, and you can measure the amount of water that is produced from the melted ice. But the ice itself is maintained at 0 degrees because it's got this outer thermal jacket which is equilibrated with ice and water. Does that make sense to you? I'll kick in a personal note here. When I was a child, one of my jobs was we made ice cream. We didn't go to the store and buy ice cream. We made ice cream. And you had a hand cranked ice cream mixer. And my job, they always put me out there to keep me out of trouble. And my job was to take a stick, and these ice cream freezers had the big external bucket. You put the ice cream in a metal container inside this, and you put the ice and salt on the outside because you have to cool it down below the freezing point of water because you're freezing the water in the ice cream. And so you have to have salt on the outside. And if the water level in that outer container gets too high, it can get salt into your product, in your ice cream. That's not convenient. So there's a hole drilled in the side of this outside container. Ours were all wooden. Okay, that's the way we were. So somebody's out there cranking away, and they're putting ice and salt around it. And my job was to stand there with a little stick and make sure that hole that the water was draining out of was kept clear so that the salt water could drain out instead of going over the lip into our ice cream. And that kept me out of trouble and gave me an appreciation for thermodynamics, I believe. There it is, folks. This all got started when I was about 6 years old playing with ice. Okay. All right, so that's the way that the system works. Now, let's just say they had to work in the wintertime because that's when you had snow. Okay. So they didn't have a way to make ice back in those days. So they had to wait till winter. They got snow. They did the experiments. And so they went forward with that. They started gathering data for about 20 years. And caloric theory was used to provide quantitative understanding of heat of reaction, etc. And it was not obvious to the modern chemical theory about bonding and composition were in the infancy. Okay. The term calorie, by the way, came out of this time period, obviously from the caloric theory, and I think it was Clement started using it. We have now sort of gotten away from calorie, which is probably a good idea. Now we just go directly to joules, which goes directly to the energy amount involved. And that sort of closed the door on the caloric theory, except for engineers. All right, now in St. Petersburg, Russia, you had this guy, Henry Hess. And Hess realized that it didn't matter what pathway you took to get to the system. In other words, this is what we call a state function. Basically, it's independent of path. So the amount of heat that's in a system doesn't matter how you got there. It's just, you eventually got there once you have defined your temperature and your pressure and your volume and the composition of the material. The amount of heat, no matter how you got there, you have the same amount of heat. Okay, this is an important concept. And we typically do this in classes with students by adding water and acids and whether you dilute it all at once or in partial dilutions and final dilutions, things like that. We get the same amount of heat. So that's the experimental result, and that's the importance of it, is that we understand that once you have defined the system in terms of its composition, its temperature, pressure, and volume, then you've got the whole thing tied down, and the numbers should be the same no matter how you got there. Okay. Now, here we have some more people involved. People started doing, that ice water uh, calorimeter is a little clunky to use and imprecise and whatnot. And so people figured out that, hey, we could do this in a constant volume bomb. Literally, we put oxygen and a chemical compound in there, and we use a tiny amount of energy in the form of a spark to set that thing off, and it literally sort of blows up inside this bomb. And everything is converted into carbon dioxide and water because we use an excess of oxygen. This works real well for organic compounds. And so we started measuring the heat of released, the heat of combustion of many different organic compounds using a bomb calorimeter. And this fellow, Berthelot, became very adept at doing that, started collecting a lot of data. And they started trying to relate those heats of combustion to the actual heats of various reactions that were not combustion. Most spontaneous reactions ended up having external or were exothermal. Okay, this was the empirical observation of primarily organic chemists who were doing bomb calorimetry experiments. And they were not conversant with physicists like Clausius, and they were not too excited about all that other stuff. So, as a rule of thumb, what came out of this work was that exothermal reactions are going to go spontaneously. But if you go back and look at certain other experiments, you realize that things do happen in which they're endothermal. For example, you could take, I think it's sodium nitrite, and dissolve it in water, and it gets cold. That's going the wrong way, isn't it? You have a spontaneous reaction, it dissolves in water, but it gets cold. So that sort of blows up this theory, but this idea of exothermal reactions being spontaneous became a very enrooted thing among organic chemists. Organic chemists are not too much into physical stuff and math, and so they became an important block. Okay, now, so the history of enthalpy as a term, apparently, obviously, Clausius was influenced by the term enthalpy, but I think it probably was not introduced into the mainstream of chemical discussion until this fellow Ornes, and I think a fellow by the name of Porter used it in 1909. Before that, they were just using the term heat. This is the heat of reaction, da da da. So the term enthalpy, which I guess the physicists, who probably knew more Greek than organic chemists knew, were using enthalpy back in the day, and they sort of, by the early 1900s, they started replacing heat with enthalpy in the literature. Now, along comes a fellow by the name of J. Willard Gibbs, who writes very baroquely. I have tried to read some of Gibbs' papers. He has hundreds of equations. It goes on and on and on. It's very, very hard for anybody to follow. If you have read anything about J. Willard Gibbs and understood it, please go to the head of the class, okay? I frankly gave up. It was like, I can't deal with this. The big thing that he ended up with was he defined a heat function, chi, which he equated to an epsilon, which is basically bond energy, plus PV. Now, this bond energy was being measured at some temperature, so it included the heat of those various processes that took those materials to that level. Now, I prefer to break this out completely differently, or at least I'm going to take what he calls epsilon, I am going to call E0, which is the bond energy at absolute zero, and this potential term UT, U as a function of T, which is what happens when you raise that to ambient temperatures or whatever your standard temperature is. Okay, And then we're going to add to that this P delta V term. All right. So in my world, the absolute energy is going to be a heat of formation, which is what he was effectively measuring up there, plus this T, the standard temperature, plus the time multiplied by the average heat capacity over the range from zero, absolute zero, to your standard temperature. This is the same equation we saw earlier, the same graphic. And it's, I think, very important to understand it. Now, the next few slides here deal with what may be a fairly arcane issue. We really can't measure H. That is to say, the heat of these processes. We can measure the change in heat, but we can't measure the heat directly. Okay. When we do these reactions at some specific temperature, T sub 0, we measure the differences, but we don't know how they relate back to the absolute heat. And that's sort of the point of the next couple of slides. And the reason I'm saying that is, let me use a different example. Suppose you've got a guy who's driving from point A to point B. You don't know how far it is from point A to point B, but you can measure his time. You know when he left, you know where he arrived at your location, and when he passed your location, you can measure his velocity. So he's going 20 miles an hour when he passes you, and you know he's been driving for an hour. So are you going to say, oh, it was obviously that he covered 20 miles? No, because he may have been driving faster or slower along the way. That's exactly the situation we have here with heat. We can measure the heat or heat capacity, that would be the equivalent to the velocity at a particular time or particular temperature, but we don't know what happened in between. And so we don't really know the energy that's there. We can't take the current heat capacity measured at some temperature, 298 degrees Kelvin, and multiply it by 298 degrees Kelvin and get the actual heat that's present in the molecule. All right, that is a concept which is hard to get across to people, and I think this example in terms of velocity and travel sort of explains the problem. You don't know if you take the current heat capacity. That is not a constant. I've said that several times through these videos. It is not a constant. It is a function of temperature. And not only that, but you have these latent heats that are built in there that don't have anything to do with the heat capacities of the individual phases. So don't make that mistake. Don't try to take the current heat capacity and multiply it by the current temperature and come up with some absolute number. It just doesn't work that way. And that is basically what the next couple of calculations show. And if you want to stop the video and look at this and read through it in detail, you may, but it sort of comes back to the same point. Okay, now what has happened is we have accepted a standard temperature, 298 degrees Kelvin, which is 25 degrees Celsius. It's about ambient temperature. It's easy to achieve in most laboratories today. So it's a very convenient place to have all of our data, since we do most of our routine chemistry in an ambient laboratory. And it's fairly easy to insulate systems adiabatically when the outside temperature is about the same as the inside temperature. So once we have done that, what we've done here is we went through there and we had to come up with some system that would cover all the elements and all possible compounds. So what we decided to do was we're going to take the most common allotrope of every element. For example, graphite for carbon. And we're going to take the energy that's in that at our standard temperature and standard pressure, 1 atmosphere, 298 degrees Kelvin. And we're going to say that is going to be 0. We're just arbitrarily assigning 0 to all those numbers. For example, hydrogen gas at 298 degrees Celsius at 1 atmosphere pressure is a gas, and we define that as as 0 heat of formation. We just arbitrarily have chosen our heats of formation based on those arbitrary numbers. Now, when once we have created that system where all the elements in their most stable allotrope are defined as 0 heat of formation at 298 degrees Kelvin and 1 atmosphere pressure. Once we've done that, we can go through and do our heats of combustion and use Hess's law, and we can build up heats of reaction for all sorts of reactions. You know, basically we get these data and we can come up with these heats of reaction. And using Hess's law, we can combine these reactions and get new reactions. So in practice, the approach which you've used today is to arbitrarily assign 0 to the enthalpy. That is the standard heat of formation, and I give it delta H sub F sub sup 0. The delta means a change, it's a relative number. H is enthalpy, F is formation, and Z, it means it's a standard number at the standard conditions at 1 atmosphere pressure and 298 degrees Kelvin. And we've ignored, when we do that, we have ignored all the energy that may have been in any of those materials at that temperature and pressure. Now, since we've done that, if we want to know the absolute enthalpy, which we call the free energy, delta G, or G, what we have to do is we have to correct our heats of formation data by subtracting out this entropy that was already there. That is to say, the current standard temperature, T sup 0, times the average heat capacity over that range from 0 to T sup 0. So that's where this equation comes from. That's why G is equal to T minus, or G is equal to H minus T delta S. The T delta S is a correction term to make up for the fact that we have arbitrarily chosen where to measure our delta H's from. And that's it. Okay, I go back, oops, I just blew through that. We go back, talk about free energy here. I just blasted through one slide, which you can go back and look at if you want to. And basically it took a while to overturn the Berthelot-Thomson principle, that is to say the assumption that exothermal reactions would be spontaneous. It took a while to overcome that. They agreed, I think about 1906, they accepted the idea. Now it turns out that if you were working at absolute 0, this would be the Nernst principle, the Nernst theorem, 1906. If you're working at absolute 0, they would be right. Exothermal processes would go spontaneously. But since you're not working at absolute 0, you're working at some standard temperature, you can't count on that being true. So we go forward here. I think if you've studied anything in chemistry lately, you recognize this equation. Here again, what we call free energy is, I call it the absolute enthalpy of a system. The delta H is typically the standard heat of formations, the change of standard heat of formations, which have to be corrected by the temperature multiplied by the average heat capacity for each material between 0, absolute 0, and the standard temperature. And we're just carrying on here with doing more calculations using the nomenclature that Clausius created. And this is a slightly different representation of all of this. If you look at this, you suddenly realize that this is enthalpy, this number from here to here, where you assume that the heat of formation was 0. And so if you look at this, delta G is delta H minus T delta S. So this graphic summarizes where the delta H, if you assume that if you assume it's 0, you miss out on this T delta S element, and then you have to correct for that to get to delta G. And I'll just emphasize that. Okay, now there's an appendix which I have not included here. I decided not to really bother with it. If you go read the book, there's a whole chapter on superconductivity and what's happening when you approach absolute zero and the electrons get involved. The electrons that may have been stuck in some upper electronic state fall into a lower electronic state. It's typically, since we don't work down there much, it's a fairly small contribution to the overall process, and we can generally get away from it. But if you're dealing with superconductivity, you probably should go read that section. All right, so this is the end of part 2. Part 3 is, I think, cleaner and neater because it's got many fewer players. The history is not nearly as convoluted. Part 3 is going to deal with statistical thermodynamics. How do we relate Clausius to Boltzmann? Now, think about this. I'll give you a little introduction. Boltzmann's basically saying, hey, the energy involved here should be a state function. It should not depend upon pathway. But Clausius over there just got through defining entropy based on the pathway. In fact, he has a unique pathway. Now, how do those two things, why does that work? Why does that unique pathway that Boltzmann that Clausius came up with, how does that square with the idea that pathway doesn't matter? Why does that pathway work? And that will be talked about in the next video, among other things. And you'll also see some very useful material related to spectroscopy, etc. All right, so have a great afternoon. I thank you for your time. I apologize for blazing through some of the history, not going into any depth and detail there. But those of you who have been exposed to thermodynamic discussions in the past suddenly should realize, hey, this delta G is just the absolute enthalpy. We're correcting these arbitrary enthalpies, these delta H formation at standard temperature, for the fact that we did not include all the energy that went into the system in the first place. That's all that equation is about. Delta G is equal to H minus T delta S. That T else is just a correction because we decided to use a standard heat of formation. All right, have a great day.